Unit 4, Centrifugal Pumps. In Unit 3 of this program, the motor, coupling, and bearing components of the pump assembly were discussed. Now the focus will be on the pump itself. This part of the program will deal with centrifugal pumps. Centrifugal pumps are versatile and have many uses around the treatment plant. This type of pump is commonly used to pump all types of wastewater flows and thin sludges. Centrifugal pumps are available in many types and sizes. The basic operation of a centrifugal pump will be discussed first. A key component is the impeller. As the impeller rotates, the liquid is pulled into the center of the pump and is expelled through the outlet under pressure. Let's look at the basic components of a centrifugal pump. Here is the casing with the inlet piping and impeller removed. This casing is also referred to as the volute. The arrow points to the shaft on which the impeller fits. This photograph shows the casing or volute, as well as the inlet, outlet, and shaft. Here is the basic diagram again. Note that the shaft and the impeller are the rotating parts. The casing and the piping remain stationary. This diagram illustrates liquid coming in the inlet. Note that there is nothing to prevent the liquid from leaking out along the shaft, as shown here. A special seal is used to prevent this leaking. There are two types of seals commonly used: packing seal and mechanical seal. The packing seal will be dealt with first. In this diagram, note the location of the packing used to provide the seal around the shaft. The strands of packing are held in place by a compression ring, and this compression ring is adjusted by the gland nuts. Tightening the gland nuts will compress the packing and reduce the leakage. Do not tighten the packing so much as to completely stop all leakage. A small amount of leakage is necessary to lubricate and cool the packing. Normal leakage should be a few drops per minute. A separate source of fresh seal water is normally supplied through a lantern ring, as shown in this diagram. If the seal water is from a source of potable water, be sure that there is a backflow prevention system, so that there is no possibility that wastewater can travel through the seal water system and enter the potable water supply. Note the 2 points, A and B, on the shaft. A flow of seal water from point A to point B is needed to prevent any of the fluid being pumped from working its way up along the shaft. Wastewater generally will contain abrasive particles which will damage and wear the shaft over time. As mentioned, the compression ring should be adjusted so that the packing is loose enough to allow a small amount of clean water for cooling and lubrication to pass, but not so loose as to allow a large flow. Every time an operator walks past this kind of pump, he or she should check for a slow drip and adjust the gland nuts as required to maintain this flow. Every so often, the packing will have to be replaced. It may be old according to the preventive maintenance program, or the packing may become so compressed that the lantern ring no longer allows the proper flow of seal water. Also, the packing may become so hard that it might score the shaft. Whatever the reason, the packing has to be replaced if adjusting the gland nuts no longer allows a desired amount of leakage. The slinger ring should also be noted. It is important because it protects the bearings. The slinger ring is located on the shaft just behind the packing area, as shown in this picture. The slinger ring prevents water from migrating up the shaft to the bearing by throwing the water out away from the shaft. The slinger is made of metal or rubber. Actually, a slinger ring could be made easily from a piece of thick rubber. Packing seals are simple and economical and are therefore used widely in dry installed wastewater pumps. However, since leakage rates must be checked and adjusted, packing seals are not suitable for submersible pumps. Mechanical seals are commonly used in submersible applications as well as in many dry well installations. Now look at the mechanical type of seal, which is used to reduce leakage around the pump shaft. There are many types of mechanical seals, so refer to the manufacturer's literature for exact details of how a certain system works. The operation of one type of mechanical seal will be discussed. Here is a diagram highlighting the basic components of a mechanical seal. Note the 2 parts of the diagram labeled A, and note that this is a cross-sectional diagram. The part labeled A is really a ring around the shaft. Refer to manufacturer's literature for specific information about maintenance and inspection and replacement of these seals. Regular checks for vibration, noise, temperature increase, and leakage are required. An O-ring provides a water seal between the shaft and the surface at A. The other ring, labeled B, is attached to the pump casing, with the bolts and solid members shown in the diagram. There is a spring that forces the stationary and rotating rings together with a given amount of pressure, keeping the wearing surfaces of the two rings in contact. An advantage of mechanical seals over packing seals is that seal water does not need to be provided. Many mechanical seals are oil lubricated. This figure shows an inner and outer seal arrangement with the oil reservoir between the two seals. There is still a small amount of leakage through a mechanical seal. Therefore, it is typical to have some fluid enter the oil housing adjacent to the mechanical seal. Follow the manufacturer's recommendations for the frequency of changing this oil. The wearing surface must be kept extremely clean. This means that care must be taken in storing and handling these seals. Keep them in their original wrapping until they are needed. As mentioned, there are many types of mechanical seals. For example, there are various spring arrangements used. The springs that keep the two wearing surfaces together may be a series of little springs like the one shown here. Other types use one large spring that goes around the shaft. Two examples of these seals are shown here. Mechanical seals may also be cooled and lubricated with seal water, as demonstrated in this figure. The label C indicates the wearing surface. Note that a floating bushing has been added. This bushing helps reduce the flow of water. If a pump with a mechanical seal is not being used, it is good to rotate the shaft slightly every day to avoid setting of the two faces. Refer to manufacturer's literature for specific information about maintenance, inspection, and replacement of these seals. Regular checks for vibration, noise, temperature increases, and leakage are required. When a mechanical seal requires replacement, either call in a mechanic, or if qualified personnel are available to change the seal, follow manufacturer's instructions. Let's again consider of seal water supply arrangements possible. This particular system includes a water line with a pressure regulator, a solenoid valve and a pressure gauge, along with shutoff valves and a bypass line. Seal water systems can also be much simpler. This example shown here has a water supply, a shutoff, and a pressure gauge. Here is a picture of one type of backflow prevention device. It was previously mentioned that the seal water should be supplied at a pressure greater than that supplied by the pump. This seal water must have a pressure at least 70 kilopascals, 10 psi, higher than the maximum volute pressure. This pressure difference is needed to force the water to flow from the lantern ring into the volute. Now, the wear rings will be considered. Wear rings are not included in all pumps. Depending on the design and the manufacturer, wear rings are generally added at points in the pump that are particularly susceptible to wear. Replacing a wear ring is usually a quick and economical way to recondition an aging pump. Sometimes there is only one wear ring, located on the suction side of the volute casing, labeled Wear Ring A in this diagram. There may also be a wear ring on the head end of the volute casing, labeled in this diagram as Wear Ring B. These two wear rings may be made of the same metal but different alloys. Wear ring B should be the harder alloy. Some manufacturers also install wear rings on the impeller. In this photograph, the arrow points to the wear ring. It is much less expensive to replace a wear ring than to replace the entire casing. Normally, the wear rings are replaced as required, or as indicated by decreased efficiency, or when measurements show that the clearance tolerance has been exceeded. The pump manufacturer normally provides clearance tolerance. This photograph shows a wear ring that has been removed from a pump. Notice the evident damage and wear. It is usually easy to see the drastic difference in the thicknesses of new and used wear rings. Now we will discuss shaft sleeves. The pump shaft and one type of shaft sleeve are identified in this diagram. The shaft should be handled with great care. If working on or around the shaft, be careful not to damage the shaft. Also be careful to avoid unnecessary force or sharp blows to the shaft. Shafts should be stored on end. If laid on a flat surface, the small bumps of the flat surface could warp the shaft. The shaft sleeves are designed to protect the shaft from erosion, corrosion, and wear at the packing box bearings, and other areas. The shaft sleeve most frequently encountered is the one installed for the protection of the shaft in the packing box. There are various types of shaft sleeves. They must fit tightly on the shaft so that the sleeve does not turn, and so there is no leakage between the shaft and the shaft sleeve. Sometimes an O-ring is also used to reduce leakage. Both the removal of the shaft sleeve and the installation or pressing on of a new shaft sleeve will have to be done in a machine shop. Note, too, that any O-ring should be replaced when the shaft sleeve is replaced. The pump casing. Most wastewater centrifugal pumps are built so that the intake is at the center and the discharge on the outside. Here is a diagram and a photograph of this typical wastewater centrifugal pump. This type of centrifugal pump is called an end suction pump. The removable cover is called the pump volute. Additional centrifugal pump types. A submersible pump is an end suction close-coupled centrifugal pump with a sealed motor that can be submerged in the fluid it is pumping. The motors are usually oil-filled and are cooled by the fluid that they pump. Since submersible pumps can be installed directly into wet wells, installations can be smaller and more economical. Leakage into the motor can cause serious damage. Most submersible motors have double seals and leakage sensing equipment that will automatically shut down the pump before damage occurs. Typically, a guide rail and a hoist will be provided to remove pumps from the wet well so that equipment can be accessed without dewatering the tank. While the end suction type of centrifugal pump is most commonly used in wastewater treatment plants, there are many other types of centrifugal pumps. In the water industry, for example, where clogging is not a consideration and high pressures must be achieved, there are a number of other popular styles of centrifugal pumps. Some other types of centrifugal pumps will now be discussed. They are less common than the types already discussed, but still may be encountered in a wastewater, water, or stormwater facility. In the split case pump, both the inlet and outlet are perpendicular to the drive shaft. As can be seen, the casing is split so the pump can be opened for inspection of the shaft, impeller, or bearings without removing any of the piping. This particular pump is called a horizontally split pump because the casing is split parallel to the drive shaft. A radially split pump has a split perpendicular to the drive shaft. Here is a photograph of another centrifugal pump called a double suction pump. On this pump, the intake and discharge are both normally below the center line of the pump. This gives greater pumping volume than the same pump with single suction. Although additional stages will not affect the amount of liquid pumped, they will increase the pressure at which the liquid is pumped. This means that multi-stage pumps are used when high pressures are required. This diagram shows a two-stage double suction pump. The suction at A is split into two and fed to the first stage impellers at B. The discharge from these impellers, C, is fed to the intake of the second stage impeller at D. Final discharge occurs at E. Next, we shall examine a line shaft turbine centrifugal pump. Here is a diagram of a line shaft turbine centrifugal pump. This pump is often used to pull water from deep wells. The line shaft turbine is really a multi-stage centrifugal pump. The pump intake is at A, and the first impeller is at B. The intake of this impeller is at C, and the discharge at D. The inlet to the second impeller, F, is at E, and the discharge is at G. The final pump discharge is at H. So far, the following components of the centrifugal pump have been discussed: packing and mechanical seals, seal water, wear rings, shafts and shaft sleeves, and the casing. The last part of the centrifugal pump to consider is the impeller. In most centrifugal pumps, the impeller looks like several cup vanes or blades mounted on a disc or shaft. The diagram illustrates how the impeller works. Notice how the vanes of the impeller force the water and wastewater into the discharge or outlet pipe. The shape of the vanes of the impeller is important. They throw wastewater out of the pump, The centrifugal pump can be run for a short time with the discharge valve closed. Note that this can only be done for a short time. If the pump is run too long with the discharge valve closed, the water inside the pump will heat up, eventually changing to steam. This steam can cause damage, and in extreme cases even cause an explosion. On the other hand, it is acceptable to partly close the discharge valve of a centrifugal pump to reduce the volume of liquid being pumped. This only applies to centrifugal pumps. The suction valve always has to be fully open. If it is partly closed, there may not be enough water going into the pump. This will cause cavitation, which sounds like a rotating bowl full of rocks. Cavitation will quickly ruin the pump. The vanes of an impeller vary. The number of vanes can change, and so can the manner in which they are arranged or constructed. Sometimes the vanes are placed between two discs or shrouds, as shown in the photograph. This kind of impeller is referred to as a closed impeller. The size of solids which can be passed by the closed impeller is dependent upon the distance between the shrouds. Another variation is to use only one disc or shroud, as shown in this diagram. This impeller is referred to as a semi-open impeller. In this type, there are no discs used. This type of impeller is referred to as an open impeller. Open and semi-open impellers are most often used to pump wastewater. Both impellers work well with liquids with a high solids content. These impellers are also generally a high-volume, low-pressure type of impeller, suitable for wastewater applications. The diagram illustrates the critical distance for clogging in the open and semi-open impellers. The size of solids that a pump with open or semi-open impellers will move without clogging depends on the closeness of the impeller to the suction side of the volute case. This distance can vary from 0.4 millimeter to several centimeters, 15 thousandths inches to several inches. This diagram illustrates a recessed impeller. In this case, the impeller is recessed or contained in a special enclosure. As seen, the recessed impeller will allow larger solids to pass through the pump without even touching the impeller. The recessed impeller pump is suitable in pumping thin sludge and will not clog easily, but the energy requirements of the recessed impeller pump are higher than for other types of centrifugal pumps. Another variation of the centrifugal pump that has been adapted to better handle solids is the chopper pump. In these pumps, the vanes of the impeller are cupped and sharpened in order to chop solids as they enter the pump. All four types of impellers, closed, semi-open, open, recessed, share an important characteristic. These impellers all cause a flow from the eye of the impeller to the outside. These impellers cause what is called radial flow, and they can be referred to as radial flow impellers. Radial flow impellers are used in most centrifugal pumps. However, there are other variations that will be noted. One variation is the axial flow impeller as shown. Axial flow impellers look like propellers and create a flow that is parallel to the shaft, called axial flow. Pumps using these types of impellers are often used in municipal water supply systems, for irrigation, or for dewatering flooded areas. Another variety. The name implies the mixed impeller is a combination of the axial flow and the radial flow impellers. The mixed flow impeller gives the liquid both centrifugal motion and motion parallel to the shaft. The mixed flow impeller is commonly used in line shaft turbines, which are used, as seen earlier, to pump water from deep wells. A type of pump that operates by a mechanism similar to that of centrifugal pumps is the disc pump. The mechanism by which these pumps move fluids is boundary layer viscous drag. Fluid enters the pump and molecules adhere to the surface of the two discs. This layer provides a molecular buffer between the fluid and the disc's surface. As the discs rotate, energy is transferred to the fluid layer by layer, and the fluid is pulled through the pump. Due to the design, disc pumps specialize in pumping liquids that have a high solids content, are highly viscous, are highly abrasive, contain very stringy materials, and or have a high air content. General pumping terms and concepts. Now, some more general pumping terms and concepts will be considered. The suction and discharge piping will be discussed first. Suction piping is the piping through which the fluid enters the pump. Discharge piping is that which carries the fluid away from the pump. Generally, the suction piping is designed to minimize friction losses and the possibility of air getting into the pump. Although some of the points to be mentioned about the suction piping are design-related, an operator should be aware of them to help troubleshoot his or her own system. First of all, the appearance and structure of the suction piping will depend on whether the liquid to be pumped is above or below the level of the pump. The diagram shows the suction pipe structure when the liquid to be pumped is below the level of the pump. These are important points to consider about suction piping when the liquid being pumped is below the level of the pump. First, note the term suction lift in the diagram. Suction lift is the term used when the level of the wastewater to be pumped is below the center line of the pump. Sometimes suction lift is also referred to as negative suction head. The ability of the pump to lift wastewater is a result of a partial vacuum created at the center of the pump. This vacuum helps move the wastewater up the pipe towards the pump. Suction lift works like sucking liquid through a straw from a glass. Sucking on the straw forms a partial vacuum, and a pressure differential is created. Pressure is reduced on the liquid inside the straw. The greater atmospheric pressure on the liquid around the outside of the straw forces liquid in the straw to move up. The maximum practical suction lift of a centrifugal pump is normally 5 to 6 meters, 15 to 20 feet. Note the foot valve at the bottom of the suction piping. It opens to allow wastewater to enter the suction pipe, but closes to prevent water from passing back out at the bottom. The foot valve should be at least one pipe size larger than the inlet piping, and it should be well below the water level to avoid any possibility of air being drawn in. Also, the foot valve should be at least one pipe diameter from the tank floor and the sides. Where elbows or other bends are required in the suction piping, they should be of the long radius type. The suction piping should be one pipe size larger than the pump inlet. The required eccentric reducer could be turned so that the top is flat and the bottom is tapered, as shown. This prevents any entrained air from building up at the inlet of the pump. Use the right type of reducer when replacing piping. A simple concentric reducer will not do. Finally, the distance between the pump and the vertical piping should be at least 8 pipe diameters to ensure smooth flow at the pump. Now, note how suction piping changes when the liquid being pumped is above the level of the pump. This diagram shows typical suction piping requirements when the liquid to be pumped is above the center line of the pump. Sometimes, this is referred to as a flooded suction or positive suction head situation. If an elbow and bell are used, they should be at least one pipe diameter from the tank bottom and sides. This is done to create the proper hydraulic conditions at the suction piping inlet. This type of suction piping must have an isolation valve, which can be used to prevent flow when the pump has to be removed. There are also some important features and concepts that should be kept in mind with respect to discharge piping. Starting from the pump, there should be a concentric reducer that enlarges the discharge pipe size to at least one size larger than the flange at the pump. The check valve prevents a wastewater flow backwards through the pump. Material moving through the pump in the wrong direction can damage both the pump and the motor. Just past the check valve is an isolation valve, which allows for removal of the pump and maintenance of the check valve. The isolation valve should be downstream of the check valve to allow removal of the pump or the check valve. Now is a good time to discuss discharge head and total head. These two diagrams show the discharge head and total head in both the suction head and the suction lift situations. In both cases, the discharge head is measured from the center line of the pump to the level of the discharged water. The total head is the difference between the two liquid levels. The total head shown in the diagrams is actually the total static head. In reality, the pump has to work harder to overcome friction losses in the piping and valves. This friction loss is added to the total static head to obtain the total dynamic head. The design-related points about suction and discharge piping, which were discussed, are ones that should be considered when troubleshooting a system. There are a few more general pumping topics to consider. Pump performance is a major concern in the wastewater treatment plant. Each pump manufacturer has likely supplied the plant with a number of pump curves that can provide information about the performance of different pumps. Here's a diagram of a typical pump curve. The pump curve is the line A to B. Use this curve to find out how much wastewater will be pumped when the head is 100 feet. To read the curve, follow the horizontal line at 100, point C, to where it meets the pump curve, point D. Then go straight down to find the discharge, point E. In this example, the discharge is about 740 gallons per minute. In metric units, the same pump curve would look like this. From the curve, we can see that when the total dynamic head is 30.5 meters, the capacity of the pump will be 47 liters per second. In order to select the correct pump for a specific application, for example, a return sludge pump, a system curve is drawn and added to the pump curve chart. The intersection point of these two lines is called the operating point for the return sludge pump in this example. Pump curves will show different pump capacities for different impeller diameters and different motor sizes. The efficiency curves have been added to the chart. These efficiency curves are important in the selection of a pump. For example, if the total dynamic head is 12 meters, 40 feet, this chart indicates that a 20 centimeter, 8-inch impeller will pump about 36 liters per second, 570 gallons per minute, at an efficiency of approximately 60%. The chart also denotes that an 18 centimeter, 7-inch impeller at a head of 12 meters, 40 feet, will produce about 12 liters per second, 200 gallons per minute, at about 53% efficiency. Often, the decision as to which impeller to use will depend on the capacity required and the application for which it will be used. Additional information, such as pump horsepower requirements, may be available on standard pump curves. These additional curves tell the designer what size motor must be provided. Information about power requirements of any given pump can be important. Thus, discussion on power requirements follows. First, the measure of power drawn is usually taken in amperes, the units of current. The voltage delivered to a motor is usually constant, but should also be monitored. Operators should be able to take amperage readings of all pump motors in their plants. Permanently installed ammeters should be continuously measuring current, or a portable ammeter should be available to regularly check current. If pumping from a wet well, the difference in water level between the full and empty wells will affect amperage readings. A good time to take amperage readings is a few seconds after the pump in the wet well starts. It would also be useful to have a flow meter on the pump as well, to give an exact idea of how the pump is operating at any time. An electrician can train personnel to use a portable ammeter to check a motor's current draw. Operators should read and record the amperage drawn by each motor on a weekly, if not daily, basis. Keeping a record of the amperage that a motor draws while the pump is running gives a good indication of what is happening. As long as the amperage stays about the same, there are no problems. In examining records for a given motor, changes in the amperage readings are the primary concern. A very slow increase in the amperage over time can be an indication of wear and tear on the motor. Resistance to the turning of the shaft caused by worn bearings, a misaligned coupling, a seal that is over-tightened, clogging in the impeller, or motor problems. A slow decrease in amperage means that less wastewater is being pumped, probably because either the seals are worn, the impeller is worn, or there is increased friction in the discharge piping from a partial clogging inside the pipe. This can best be explained by considering the 23 centimeter, 9-inch impeller for the pump curve shown, which shows the pump delivering 55 liters per second, 880 gallons per minute, against a 17-meter, 55-foot head. If the discharge head is increased by 1 1/2 meters, 5 feet, because of additional friction losses or throttling of the discharge valve, then the discharge is decreased to 42 liters per second, 660 gallons per minute. Since it takes less power to pump 42 liters per second, 660 gallons per minute, at 18 meters, 60 feet, than 55 liters per second, 880 gallons per minute, at 17 meters, 55 feet,
The amperage decreases as the head increases.
A sudden large decrease in amperage means that little or no wastewater is being pumped. An impeller may be loose or completely eroded, or there may be a blockage in the discharge piping. A blockage in the discharge piping may simply be a closed valve. While it is not a recommended practice, some operators actually control the flow by throttling the discharge valve. A better operating procedure is to only close the discharge valve to isolate the pump. If flow throttling is practiced, this will have a noticeable effect on pump motor amperage readings. The current required by a motor when a pump is starting is much larger than that required just to keep the motor running when it's already at maximum speed. To avoid a large current being drawn on startup, some large high-pressure pumps are started with no load. That is, no water is pumped until full motor speed is reached. This type of startup system is usually automated. Now, let's look at different pump configurations. Pumps can be arranged in series or in parallel. A series arrangement is more common in water treatment facilities. Parallel arrangements are more common in wastewater treatment plants. Some diagrams to contrast these two arrangements follow. This diagram shows pumps arranged in series, as might be done in a water treatment facility. In a series arrangement, the discharge from one pump becomes the intake for the next pump. Discharge pressures are additive, while the capacity remains the same as for a single pump.
Let us look at an example of how pumps in series work together. Here is a performance curve for a single pump that can move 63 liters per second, 1,000 gallons per minute, at 5 meters, 16 feet, and which we will refer to as Pump A.
Two other pumps, Pump B and C, identical to Pump A, are purchased. The three pumps are installed in series, as shown in this figure. Now the curve for pumps A, B, and C operating together has been added. Note that each point on the new curve is found by taking the capacity of one pump, but adding the pressures from the three pumps together. When pumps A, B, and C operate in series, the operating point is 93 liters per second at 8.5 meters, 1,450 gallons per minute at 28 feet. This diagram shows three pumps, A, B, and C, in parallel. This arrangement is common in wastewater treatment plants. When pumps are arranged in parallel, they could each have individual suction lines, or they could share a common suction header. With a parallel pump arrangement, the output capacities will be additive, but the discharge pressure will remain the same.
Let us look at an example of how pumps in parallel work together. Again, we will start with a single pump, Pump A, which can move 63 liters per second at 5 meters, 1,000 gallons per minute at 16 feet.
Two other pumps, which are identical to Pump A, are purchased and labeled Pump B and Pump C. The three pumps are installed in parallel as shown here. Now the curve for pumps A, B, and C operating in parallel has been added. Note that each point is found by taking the pump pressures as they are and calculating new capacities by adding together the individual pump capacities. When pumps A, B, and C operate in parallel, the operating point is 110 liters per second at 7 meters, 1,750 gallons per minute at 23 feet. As you may have noticed, the terms discharge head and pressure are used interchangeably when discussing pump performance. There are direct conversion factors between head and pressure measurements. Considering metric units, 1 meter of head is equivalent to 10 kilopascals. Using English units, 2.31 feet of discharge head is equivalent to 1 psi. The next term to introduce is cavitation. Cavitation is the term used to describe the action of an operating centrifugal pump when it is attempting to discharge more water than suction can provide. This can occur when a centrifugal pump is operating at a capacity higher than its design condition, the suction line is undersized, or the suction line is partially blocked with debris, or a partially closed valve. When a centrifugal pump operates under these conditions, An area of very low pressure can form around the impeller. If pressure falls below water vapor pressure, then vapor bubbles can form in the water. As the water moves through the pump, the pressure increases, which causes bubbles to suddenly collapse with enough force to actually gouge small pieces out of the impeller. The formation and collapse of these bubbles is called cavitation. Cavitation can also be caused by the action of the edges of the impeller. Pockets of low pressure can be created by the action of the vane tips or outer edges of the impeller. This can be corrected by increasing the casing pressure or lowering the speed of the impeller. In addition to pitting of the impeller, noise and vibration will be generated. The noise will resemble that of a bowl of rocks being shaken. If cavitation is not corrected or prevented, there can be serious mechanical damage to the pump. Here we see an impeller damaged by cavitation. Earlier in the program, a picture of a worn wear ring was shown. It was damaged by cavitation as well. Cavitation can cause damage or premature wear to the pump components as well. As soon as cavitation is noticed, corrective steps should be taken. If a pump has been operating normally and then becomes noisy due to cavitation, suspect suction blockage. There might be grease buildup, debris blocking the line, or a suction valve may be partially closed. In this section, the operation of centrifugal pumps will be the main focus. A number of operator responsibilities regarding centrifugal pumps have already been mentioned. Let's see how many of them you can recall. In inspections of the plant, what sensory information or checks will be performed on the pumps? What readings will be taken and recorded on a regular basis? Sensory checks for normal operation should be made of each pump every time it is passed. Be alert to
any unusual vibration. Check to ensure that bolts and fasteners are not working loose.
There are readings to and discharge gauges. Check the lubricant levels. Check and adjust the seal water leakage rate. Observe and record flow rates. Take and record records of pump operation and maintenance. Other regular operational functions relating to pumps that operators perform include pump startup, including priming, changing pump sequence, and unclogging the pump. There are also maintenance activities, which we will discuss later. These maintenance activities include maintaining proper lubrication, in addition to checking and replacing packing, mechanical seals, impellers, wear rings, and so on as required, checking the alignment and adjusting as required, and cleaning and repairing motors, couplings, bearings, and pumps.
The 3 pump startup functions will be examined next. Let's start with pump priming.
A pump will not operate unless it has been properly primed. A pump is considered primed when the pump casing and the suction piping are completely filled with liquid. The pump in this diagram is not primed because the pump casing is not completely filled with liquid. Note the vent at the top of the casing. Simply opening the vent will release the air trapped in the casing. In order to prime this pump, a vent at point A is needed to release the air from this high point. Opening the vent should allow the pump and piping to fill. Let's see what steps are involved in priming a pump. Starting with a flooded suction pump. This pump is under pressure. It has a positive suction head. A pump in this arrangement will seldom lose its prime, and will likely only need to be primed after it has been opened or replaced. Now, we will review the procedures used to prime a pump that draws from a liquid level below the center line of the pump. A pump installed in this type of situation is said to have negative suction head. This diagram shows one type of arrangement used in negative suction head installations. The foot valve holds the water in the pump and suction line after the pump has been initially primed.
The priming procedure is as follows. Open the suction line valve, if there is one. Open vents at the highest points on the pump casing. Fill the pump casing with an independent supply of liquid. If the discharge line is full, simply open the vent and check valve to allow the pump casing to fill. Close the vents when water starts to run out of them. Start the pump.
Here is an alternative method of priming pumps with negative suction head. Close the discharge valve. Open the inlet valve. Start the pump with a dry casing. Open the vacuum valves to pull air out of the pump casing and draw water through the intake. As the water fills the pump casing from the intake, motor amperage will increase. At a predetermined amperage draw, the discharge valve is opened. Vacuum valves are closed and the pump is operational. Here, a bypass line allows the water that has already been pumped to flow back around the check valve. This ensures that the pump prime is maintained. In this example, a separate water supply is used to fill the pump when it must be primed. Other pumps are referred to as self-priming pumps because they can, as the name states, prime themselves. A self-priming pump is easily recognized by the large chamber at the top of the pump. This chamber is an air separator. The air separator ensures that the air that is in the pump when the pump is started will be removed through the discharge line. There are two cycles involved, the priming cycle and the pumping cycle. In the priming cycle, the air-water mixture A is pumped through the discharge neck B into the air separator D. Here the water drops out of the mixture and falls back into the chamber. The air is pumped out through the discharge C. Once all the air has been removed, the pump is in the pumping cycle. The water is pumped to the air separator and the discharge through two paths, as shown in the diagram. Let's now consider helps prevent the situation where the standby pump is idle for a long period of time and then does not start when it is needed. Note that this pump sequencing is not necessarily designed to provide equal wear to the pumps. If both pumps get equal wear, there is the possibility that both pumps will wear at the same time, leaving none available to do the job. Instead, use some method of providing unequal timing periods, such as a 2-to-1 ratio, a timer, or by manual switching. An hour meter and pulse or start counter on each pump could provide an accurate check on the amount of use each pump is receiving. In this picture, note the hour meter used to keep track of pump usage. Another operational function that an operator should be familiar with is how to unclog a pump. While centrifugal pumps are designed for minimal clogging, they sometimes do clog, especially if stringy material is being pumped. Most centrifugal pumps have cleanout holes on the suction side of the pump. These cleanouts can be opened if the pump becomes clogged. The first thing to do when unclogging a pump is to tag out and lock the motor in the off position at the electrical panel. If the valves are motorized, a lockout-tagout procedure is also recommended for the valves. Drain the pump and then remove the cleanout hole cover to remove the debris. After the cover is replaced, be sure to prime the pump before it is restarted. This section will consider some of the maintenance responsibilities for centrifugal pumps. The most important guide to centrifugal pump maintenance is the manufacturer's literature. Each operator will determine their maintenance schedule and requirements using this information at their own plant. Note also that the replacement of certain major pump parts like the impeller, sleeves, wear rings, and bearings requires special tools and special training. Call for expert assistance if a major pump part needs to be replaced. Besides these manufacturer-specified maintenance requirements, remember the importance and value of an up-to-date maintenance record system. Keeping a formal record system for pumps and valves will make it easier to check that all necessary maintenance is done on schedule. A record system also allows the examination of the maintenance history of any piece of equipment. Cleaning and corrosion control are other important aspects of any maintenance program. Because the life of a lubricant is greatly affected by the amount of dirt, dust, scale, and moisture that get into it, a regular cleaning program should be put into effect. This cleaning program should include the cleaning of all areas with high-pressure air or water without damaging motors and other equipment or injuring personnel. Additionally, the program should include the cleaning of floors, removal of rust on metal surfaces, and repainting of all surfaces. Major centrifugal pump maintenance items are the packing seal and the mechanical seal. The next section will cover the packing seal. For normal operation, the leakage rate through the packing should be between 5 and 20 drops per minute for a 2.5 centimeter, 1-inch shaft, and 10 to 20 drops per minute for a 5 centimeter, 2-inch shaft. When it is no longer possible to adjust the leakage to the desired rate, it is time to change the packing. Note that packing is also changed as part of scheduled preventive maintenance. Normally, packing is changed at regular intervals or after a certain number of hours of pumping. This avoids the possibility of old packing becoming hard and scoring the shaft, even though a proper leakage rate can still be obtained. Packing is designed to wear, and it will deteriorate with time. Some of this deterioration is caused by the loss of lubrication in the packing material. This is normal and to be expected. Sometimes, however, the packing may appear to fail prematurely. If that happens, try to determine the cause. There are generally 4 things that cause premature packing failure: improper packing type or size, excessive amounts of abrasive material. Additionally, poor mechanical condition from excessive wear, poor alignment, loose base bolts, imbalance, and so on. Loss of seal water or packing lubricant. There is a specific procedure to be followed when replacing a packing seal. Turn off the main circuit breaker for the pump. Lock the circuit breaker in the off position and tag it off. Close the suction and discharge valves to isolate the pump. Lock out and tag out the suction and discharge valves if they are electronically activated. Open the drain valve to release the pressure. Drain the pump by loosening the bolts on the handhole cover. Do not remove the bolts completely until the pump stops draining and the shutoff valves are holding. Remove the packing gland nuts and/or bolts and remove glands. These are usually split for removal. If the packing gland is not split, it has to be backed off on the shaft. Be sure to provide room for removal and replacement of packing. Now remove the packing. There are a number of special tools available to help you do this. The packing rings can be removed by screwing a packing hook into them and pulling them out. It may help to revolve the shaft slowly by hand while pulling. Care must be taken using a packing hook so that the shaft is not scored or nicked. After removing the top rings of packing, the lantern ring must be removed. This may be fished out with a heavy piece of wire, coat hanger, or welding rod. Some lantern rings have a threaded hole in which a 6 mm quarter-inch bolt can be inserted. If the pump has been in service for a while, clean around the shaft and stuffing box to remove the lantern ring. A tap with a wooden dowel may be necessary to loosen it. Next, remove the remaining packing rings. Count the number of rings on each side of the lantern ring. Never leave any old packing. It must all be removed. Adding new packing on top of old can cause the old packing to score the shaft. Wash all parts with soap and water and scrub with a wire brush if necessary. Thoroughly clean the inside of the stuffing box and the shaft. Wipe the parts dry. Do not use solvents for cleaning because they may interact with chemicals in the packing and cause premature failure. Disconnect the seal water line. Make sure that the seal water hole through the stuffing box is clear and clean. Check the shaft and sleeve for wear. This can be done by visual examination or by sliding the packing hook along the shaft, feeling for roughness. Check the interior of the stuffing box for roughness due to corrosion or wear from the packing. If excessive roughness is found, then the interior surface should be remachined before being reinstalled in the pump. There are different types of packing materials available. Check your manufacturer's literature to determine what packing type, size, and number of rings of packing a particular pump will require. Packing should be kept in a clean place. Never allow the protective wrapping to be left off or the box uncovered. Do not allow the packing to come in contact with solvents or high temperatures, which could force the lubricant out of it. Discard any packing that has become contaminated with dirt, sand, grit, or other foreign material. Packing can be purchased by the roll or in individually cut rings. When using coil or spiral packing, always cut the packing into separate rings. Never wind a coil of packing into a stuffing box. Rings can be cut either with butt joints or with diagonal joints. The best way to cut packing rings is to cut them on a dowel the same diameter as the shaft in the stuffing box area. If there is no shaft wear, rings can be cut on the shaft outside the stuffing box if there is room. The packing should never be laid out straight on a board and cut. This will result in a joint that will not seal. Each ring can be cut in the same manner, or the first ring can be used as a master from which the balance of the rings are cut. It is important that the rings be cut to the correct size. If they are not, service life is reduced. This is where die-formed rings are useful. They give you the exact size ring for the outside of the shaft and the inside of the stuffing box. Also, there is no waste because of incorrectly cut rings. Install one ring at a time. Make sure that the ring is clean and has not picked up any dirt. Lubricate the ring with Teflon grease or another appropriate lubricant. Successive rings of packing should be rotated 90 degrees so that the joints are a quarter turn apart. Each ring should be seated with a wooden block or split sleeve. When the lantern ring and enough packing rings have been individually seated so that the nose of the packing gland will reach them, individual tamping should be supplemented by the gland.
After the last ring has been installed, hand tighten the bolts to very slightly snug. Do not jam the packing into place by excessive gland loading. Gland bolts should be tightened evenly.
If the pump system has an external water seal, the seal water should be turned on now, prior to starting the pump. It should be allowed to leak out of the stuffing box for a few minutes to flush out any grit or foreign material. Start the pump and allow it to run about 15 minutes before adjusting the gland nuts. Adjust the gland evenly. Allow ample time between adjustments for the pump to respond to the change in pressure, about 15 minutes, or until the leakage level's off. Check the stuffing box to be sure that there is no increase in temperature. If the temperature rises, loosen the packing gland until the temperature drops. Then tighten the gland carefully to control the leakage. Examine the old packing set that was just removed. Do not throw the set away. This old set can provide clues about condition of equipment and possibly indicate how the problem can be solved. Problem: excessive reduction in cross-section of packing directly below the shaft. Possible trouble: shaft riding on packing. In service, early leakage occurs around the top of the shaft. Problem: excessive wear of packing directly over or on either side of the shaft. Possible trouble: shaft out of alignment, causing badly worn bearings and whipping of the shaft. Problem: part of one or more rings is missing from the set. Possible trouble: bottom of the stuffing box is badly worn, with packing being extruded into the system. Problem: axial bulge in one or more rings. Possible trouble: adjacent rings cut too short or too long, causing packing to deform under pressure. Problem: packing shows tendency to sheet out or extrude between the shaft and the gland. Possible trouble: excessive gland bolt pressure, too much clearance between the shaft and the gland. Problem: rings next to the gland are badly deformed, while those farther away are in fair condition. Possible trouble: improper installation of packing and excessive gland bolt pressure. Problem: wearing face of rings is dried and charred, while the rest of the packing is in good condition. Possible trouble: high temperatures and lack of adequate lubrication with over-tightening of the packing or mislocating the lantern ring. Problem: innermost ring is deteriorated. Possible trouble: packing is incompatible with the liquid being handled. Problem: excessive score or wear on the shaft. Possible trouble: hard packing or wrong type of packing. Personnel will also be responsible for maintenance of mechanical seals. Let's see what is involved. The first step in replacing mechanical seals is to be able to determine when a new mechanical seal might be required. Mechanical seals cannot be routinely inspected. This is because, in operation, the faces of the mechanical seal wear in with respect to each other. If they are disturbed, it will not be possible to reseat them. Generally, a mechanical seal must be replaced when changes in vibration, noise, temperature, or leakage rate are noticeable. Any of these signs is an indication of excessive wearing of the surface. Factors other than normal wear and tear and scheduled maintenance may cause the failure of a mechanical seal. Each of these points is expanded on in the next section. A mechanical seal might fail because of misalignment. Misalignment can be caused by excessive vibration of the motor and pump, or improper installation of either of the units, or the mechanical seal itself. If the seal is installed so that mating faces are not parallel to each other and perpendicular to the shaft, the rotating face will try to square itself with the seat, causing uneven wear on the mating surface. To prevent this problem, the seal must be properly installed. The rotary unit must run parallel with the shaft, and the stationary seat must be perpendicular to the shaft. The mechanical seal could fail because of lack of lubrication. To operate properly, the mating faces of the mechanical seal must run on a liquid film. If there is no film, the seal will overheat and fail. In some mechanical seal failures, overheating and lack of lubrication go hand in hand. If the hard face is subjected to extreme heat, it will expand. This will result in thermal cracks on the face of the seal. Abrasive damage can cause mechanical seal failure. When small abrasive particles work their way between the seal faces, they may groove the mirror finish of the faces, or they can leave deposits from evaporation of the liquid. When these deposits build up on the shaft, they will freeze the sealing elements to the shaft and eliminate all shaft flexibility. This condition can be especially severe when Teflon sealing wedges are incorporated in the seal. Corrosion is another cause of mechanical seal failure. Corrosion failure is easily recognized in most cases. Metal parts show signs of pitting, or sections are corroded away. To reduce effects of corrosion, use the appropriate quality of seal for the pump. If in doubt of which of two possible seals to use, select the better quality seal. For whatever reason, operators are sometimes required to change a mechanical seal. Since there are so many different kinds of mechanical seals, the best guide on how to replace the seal is the manufacturer's literature. However, there are some general points to be made. Mechanical seals are very fragile and can be easily damaged. They should be handled with great care. If one of the faces is dropped on the floor, do not install it. The interfaces must be very clean. If a face should become soiled, it should be washed with water only. Used faces can be reused if they are returned to the manufacturer for refinishing. Whether this is cost-effective will depend on the size of the seal. So far in this section on maintenance of centrifugal pumps, the following key points have been made. The importance and value of keeping an up-to-date maintenance record system were stressed. The requirement for cleaning and corrosion control was indicated. The signs that indicate when a packing seal has to be replaced, causes of packing seal failure, and procedures for replacing a packing seal were discussed. And the signs that indicate when a mechanical seal has to be replaced, causes of mechanical seal failure, and care to be taken when replacing a mechanical seal were described. To close the discussion on centrifugal pumps, this last section will provide a generalized centrifugal pump troubleshooting guide. This guide lists possible causes of a number of different pump problems. Problem: the pump fails to deliver liquid. Possible causes: the pump is not properly primed or vented. The discharge and/or suction valve is not open. The check valve is jammed shut. There is a high spot or air pocket in the suction line. Problem: the pump flow rate is too low. Possible causes: there is an excessive suction lift or inadequate submergence of suction. The impeller is clogged. Problem: pump capacity is below rating. Possible causes or remedies: check all of the points listed for the situation when a pump fails to deliver fluid. In addition, check for insufficient vacuum created inside the pump, entrained air or gas in the liquid being handled, worn wearing or seal rings, damaged impeller, defective packing of the shaft seal. The foot valve on the suction line is too small. The check valve is not operating properly. The direction of the impeller rotation is incorrect. The impeller is mounted backwards on the shaft. Problem: loss of prime. Possible causes: an air leak in the suction piping or stuffing box, excessive suction lift, or insufficient submergence of the suction intake, and entrained air or gas in the liquid being handled. The water seal in the stuffing box is not functioning. A defective foot valve. Problem: vibration and noise. Possible causes: shaft misalignment, an unstable pump base. Material in the pump is causing an imbalance. Cavitation, worn bearings, a damaged impeller is causing imbalance. There is a loose valve fitting in the line. There is a blockage in the suction side. The shaft is bent. A coupling is worn or damaged. The pump is not properly primed. The suction lift is too high. Problem: overheated bearing. Possible causes: there is too much grease in the ball bearing, or insufficient oil, or the wrong type of lubricant is used. There is abnormal end thrust. There is dirt in the bearings. There is excessive belt tension. Problem: pump overheats and kicks out because of overload of the driver. Possible causes: pumping is over capacity because the existing head is lower than the rated head. Packing is too tight or is defective. The shaft is bent. There is misalignment. Bearings are faulty. Uneven gland adjustment. Wearing ring tolerances too close. Foreign object inside volute. Clogged impeller. Problem: pump kicks out. Check for visual damages and alarms or shut valves. If cause of failure can't be found, start motor and monitor amperage, temperature at seals, vibration, flow, noise, seal water, and discharge pressure.